Alright, this is a review of a sample of some of the application problems involving derivatives and integrals throughout the course. This one here is an example of using derivative to find velocities and positions. So this is from chapter 2. It's thrown with an initial velocity from a height of 320 feet. Now, using this information, it was taught back in chapter 2 how to find what's called the position function. Now that's usually given the letter s. S of t is equal to negative 16 t squared. That's always, assuming this ball is thrown from Earth, this is the effect of Earth's gravity, negative 16 times t squared. Now you add the initial velocity, and we're adding it because the ball is thrown away, it's thrown upward. If this had been thrown downward with that initial velocity, you would have subtracted the initial velocity, but since it's thrown upward, it's counteracting Earth's gravity. And then if there is an initial height, you add the initial height. So this is the position function. To find the velocity, though, at time equals 2, you have to have the velocity function. Well, the velocity function v of t is equal to the derivative of the position function, which is negative 32t plus 128. So if you want to find the instantaneous velocity at time equals 2, it's negative 32 times 2 plus 128. That's equal to 64 feet per second. How long does it take the ball to reach its maximum height? If we take a look at the position function here, negative 16t squared plus 128t plus 320, if we were to graph that, it's a upside down parabola. The vertex then would be the maximum height, because the x-axis here is time, the y-axis here is the height of the ball. So at the vertex of this, if you drew a tangent line, it would have a slope of 0. So we need to figure out when the velocity is equal to 0. So we take the velocity function v of t and find out when is it equal to 0. So negative 32t plus 128 is equal to 0. If you add 32t to both sides, you get 32t equals 128. So t is equal to 4 seconds. So it takes 4 seconds for the ball to reach its maximum height. What is the velocity of the ball when it hits the ground? Well, we don't know when it hits the ground, therefore we can't find the velocity. We need to know a specific time value. Well, it hits the ground when its position is 0, or the height. So we need to solve the equation s of t equals 0. So that's negative 16t squared plus 128t plus 320 equals 0. If we factor out a negative 16, that becomes t squared minus 8t minus 20 is equal to 0. This factors into t minus 10 times t plus 2 is equal to 0. So t is equal to 10 and t is equal to negative 2. Now, time can't have a negative value here, so this one is the only one that makes sense in the context of the problem. So at 10 seconds, now we find the velocity at 10 seconds. That's negative 32 times 10 plus 128. This is negative 320 plus 128, which equals negative 192 feet per second. Okay, question 2 is asking us to find the rates of change of cost and revenue. This is another application of the derivative. The derivative can either be a function that allows you to find the slope of a tangent line, or it can describe a rate of change. So find the rates of change of the cost. That's dc with respect to time. It's wanting to find out how how the cost changes as time changes. So it's dc over dt, and we need to find dr over dt. And the reason that we know it's going to be with respect to time is because there's a rate here. It's increasing at a rate of 150 units per week. So we already have a rate of change here that's measured in terms of time. So dc dt, if we have c here, 125,000 plus 0.75x, then dc dt, now we're taking the derivative with respect to time and not with respect to x, so this is going to be an implicit differentiation. So the derivative of a constant is still 0. The derivative here is going to be 0.75 dx dt. Now this comes from section 2.8, which is called related rates. We're asked to find one rate here, dc over dt, but we're going to have to use another rate, dx over dt. Now x is units, so dx dt is the change of units per week. Well, it's changing at a rate of 150 units per week, so dx dt is equal to 150, and then here production during one particular week is 1,000 units, so at that moment x is equal to 1,000. So then dc dt is equal to 0.75, which is 3/4, times dx dt, which is 150. So this is equal to 3 times 150 is 450, divided by 4 is 225 halves, and that's in dollars per week. Now dr dt, if r is equal to 250x minus 1/10 x squared, then dr dt is equal to 250 dx dt minus, now if we take the derivative of this term, you drop the 2 down in front, that becomes 2/10, which is 1/5, times x times dx dt. Now if you factor out a dx dt, then that becomes 250 minus 1/5 x. Now substituting the known values, dx dt is 150 and x is 1,000. This becomes 150 times 250 minus 1/5 of 1,000, which is 200. This is 150 times 50, which is $7,500 per week. So the change in cost is roughly $112.50 per week. The change in revenue is $7,500 per week. Okay, question 3, the point of diminishing returns. This was an application of the second derivative. This was in section 3.3, I believe, where it talks about concavity and the second derivative test. So we need to find the second derivative. The first derivative of this r function is negative 12/9 x squared plus 8x, which reduces to negative 4/3 x squared plus 8x. Now the second derivative is equal to negative 8/3 x plus 8. Now the point of diminishing returns is going to be a point of inflection. A point of inflection comes when the second derivative is equal to 0. So we need to solve this when it equals 0. So negative 8/3 x plus 8 is equal to 0. That means 8 is equal to 8/3 x. If we times by 3/8, and the 8's cancel, and here the 3/8 and 8/3 cancel, so x is equal to, not 8, x is equal to 3. Now to really prove this is a point of inflection, we have to prove that the concavity changes. At that point, x equals 3. So if we test r double prime at some value less than 3, 2 for example, it turns out to have a positive value. If we test a double derivative at some point larger than 3/4, for example, that would turn out to have some kind of a negative value. So it turns out here that we've shown that the concavity, this is concave up, and then it switches to concave down. So this is a point of inflection, and this is the point x equals 3, but it's in terms of thousands of dollars spent in advertising. So the point of diminishing returns is x equals 3, so that's $3,000 should be spent in advertising. Okay, question 4. What price will yield a total maximum revenue? So we have been given no revenue function in here to work with, but what was taught was that revenue, this is from section 3.5, revenue is equal to x times p, where p is the demand function. We haven't been given a demand function either, but we have been given information regarding the demand. The demand function is a function in terms of x and p, where x is units and p is price. So 15 units per week for $40, but a price increase of $2, so that's $42. Demand dropped to 12 units per week. So assuming this is linear, we can describe this using a linear equation. The change in y is 2, the change in x is -3, so the slope is -2/3 of this function. And if we're going to make a function in terms of x, we're going to have p is equal to -2/3 x. But what we don't know is this b value. Okay, if we want it to be y equals mx plus b form, we know the slope is -2/3, but we don't know b here. So we can choose an x and a p value already given to us, 15 and 40 for example, and that will allow us to solve for this unknown value. So 40 is equal to -2/3 times 15 plus that unknown value. 3 into 15 is 5, 5 times -2 is -10. If you add 10 to this, then 50 is equal to that unknown value. So the demand function is p equals -2/3 x plus 50. Now we can take this, plug it into here, and get our revenue function by taking demand and timesing it by x. So revenue is equal to -2/3 x squared plus 50x. Now to maximize revenue, we need to find the derivative and set it equal to 0. So it's going to be -4/3 x plus 50. If we set this equal to 0, we're going to have 50 is equal to 4/3 x. So times by 3/4 times by 3/4. So x is equal to 50 times 3/4, which is 75 halves. But the question is asking specifically what price will yield the maximum total revenue. This is how many units have to be sold. So the price is -2/3 times the units, which is 75 halves, plus 50. So 2's cancel here. -75 divided by 3 is -25, so p is equal to -25 plus 50. So that's $25. If they set the price at $25, the demand will go up significantly, and that'll make the revenue go up. So a similar situation here, except the demand function has already been given to us, and the cost function has already been given. We don't have to generate our own functions here. When the profit is maximized, what is the average cost per unit? So I guess we do have to build a profit function. Profit is equal to revenue minus cost. Revenue is equal to number of units times the demand for that unit. So this is x times 24 over the square root of x. And this is equal to 24 times the square root of x. That's the revenue now. So the profit is going to be the revenue, which is 24 square root of x minus the cost, which is 0.4x minus 600. Now, when a profit is maximized, so now we're supposed to maximize this profit. That means we have to take the derivative p prime and set it equal to 0. So if we think about this instead of the square root of x as x to the 1/2, then this becomes 24x to the negative 1/2, and we would have to drop down the 1/2. So it's 1/2 times 24, and then the derivative of this is negative 0.4. The derivative of constant is 0, so the derivative of the profit function is 12 over the square root of x minus 0.4. Now this equals 0. To set this equal to 0, we're going to have 12 over the square root of x equals 0.4. Now 0.4 is 4/10, which is 2/5. So if we cross multiply here, we're going to get 60 equals 2 square roots of x. Square root of x is equal to 30. So x is equal to 900. That's units, number of units. The average cost, C bar, is equal to cost over x. So this is equal to 0.4x plus 600 all over x, which is 0.4 plus 600 over x. This is 0.4 plus 600 over 900, which is 2/3. And again, 0.4 is 2/5. 2/5 plus 2/3 is equal to 16/15. Okay, question 6. We've been given some information about demand, so we're going to have to build a demand function again. And we're given a cost function. Assuming the demand is linear, find the profit as a function and approximate the change of profit for a 1 unit increase in sales when x equals 280. This is marginal analysis, is what this is. So they want us to approximate the change in profit. So that's dP. Now they're not asking for a rate of change of profit. They're not asking for dP over anything like dP over dx. They're asking for just the change in profit. Now dP over dx, that's just P prime. But dP, if it's just plain dP, then we can multiply both sides by dx. So the change in P is equal to P prime times dx. So we need to find the derivative of the profit function and then multiply that by dx. Now dx is a change of x. Now x is a unit, and dx is a change or a change in units, and it says approximate the change of profit for a 1 unit increase in sales. So this is a change of x. That's dx right here. So we can say that dx is equal to 1 when x is equal to 280. We already know that. So what we need to find is the derivative of the profit function. And first we need to find the profit function. Well, profit is equal to revenue minus cost. We've been given cost, but we don't know the revenue. Revenue is equal to x times the demand. So the demand function, assuming it's linear, there's a demand of $300 per month when the price is $25. It goes up if there's a drop in price by $5. So the change in y is -5, the change in x is 100. So the slope is -5 100ths, which is -1/20. Now we want to make a function y equals mx plus b. We know the slope is -1/20. We can use an x value of 300, for example, and a y value of 25 to find this unknown b value. -1/20 times 300 is -15. If you add 15 to 25, you get 40. So 40 is equal to b. So the demand function p is equal to -1/20 x plus 40, so revenue is equal to x times the demand, so it's negative 1/20th x squared plus 40x. Now profit is equal to this revenue, negative 120 x squared plus 40x minus the cost, so minus 17x minus 275. So profit, if we combine these two middle terms here, is negative 1/20th x squared plus 23x minus 275. Now the derivative is, if we drop down this 2 in front, it becomes negative 2/20th, which is negative 1/10 x plus 23. So then the change in P is equal to negative 1/10 x plus 23 times dx. Now, that means dP is equal to negative 1/10 times the x value of 200. Oh, you know what? I just remembered there was a typo in this problem. I'm sorry. Question 6. This x value is incorrect. It should be x equals 28. So this is negative 1/10, not times 280, it's negative 1/10 times 28. Apologize for that typo. Plus 23, and that whole thing needs to be multiplied by the change in x, but it's a 1 unit increase in sales, so dx is equal to 1. And negative 1/10 times 28 is negative 28/10. Plus 23. So this becomes negative 14/5. And then 23 in terms of fifths is 115 fifths. So this is 101 over $5. That's the change in profit with a 1 unit increase in sales when x is equal to 28. Okay, this is an application of the integral. The consumer and producer surplus was in the section in chapter 5. I can't remember the specific section number, but it's the area bounded between two graphs. So if we're thinking about what's happening graphically here, we have a demand function and a supply function here. We need to find this, what's called the point of equilibrium. So we need to find the x value, which is the number of units, and the price at which that occurs. So to find that, we set the two functions equal to each other, demand and supply. So 200 minus 0.4x equals 100 plus 1.6x. This becomes equation 100 equals 2x. So x equals 50. Now the price, using that value of 50, can be found using either the supply function here or the demand function. Demand function 200 minus 0.4 is just 2/5 times 50. 5 into 50 is 10. 10 times 2 is 20. 200 minus 20 is 180. So what we're looking for is what's called consumer and producer surplus. Consumer surplus is this area beneath the demand function and above a price of 180. So consumer surplus then is the integral from 0 to 50 of the demand function 200 minus 2/5 x minus the price of 180. So that becomes the integral from 0 to 50 of 20 minus 2/5 x. So that becomes 20x minus 1/5 x squared. And that needs to be evaluated from 0 and 50. So this is going to be 200 or 20 times 50 20 is 1,000 minus 1/5 of x squared. Now 50 again, x is still 50. 50 squared is 2,500. A fifth of 2,500. So we have 2,500. Divide that by 5. That's 500. So it's minus 500, and now we subtract this antiderivative here, evaluated at 0, but it's just going to be 0 minus 0, which is 0. 1,000 minus 500 is 500. So the consumer surplus is $500. Now the producer surplus is this area here underneath the price of 180 and above the supply function. So that's an integral still from 0 to 50, but now 180 is the top function, and we subtract the bottom function, which is 100 minus 1.6x dx. So this becomes the integral from 0 to 50 of 80 minus, now 1.6 is 16/10, which is 8/5 x dx. The integral of that is 80x minus 8/5 x squared over 2, which is 8/10, so that's 4/5 x squared, and we need to evaluate between 0 and 50. Now, 50 times 80 is 4,000, and 50 squared is 2,500. A fifth of that is 500 times 4 is 2,000. So this becomes 4,000 minus 2,000. Then we minus the antiderivative evaluated as 0, but that's just going to be 0. So it's 4,000 minus 2,000, which is $2,000. That's the producer surplus.